Welcome back to another video on Calculus 1. In this video, we're going to talk about the product rule, the quotient rule, and then some derivatives of trigonometric functions, along with higher order derivatives. So let's get started. First one is product rule. So what if we want to take the derivative of a product? So maybe we have a function f of x times g of x. Well, there's a rule for that, and it's the first function times the derivative of the second plus the second function times the derivative of the first. So what I want to do for you next is prove that so you can see where this rule comes from. And then we're going to work some examples. So what we're trying to prove is that the derivative of, and I'm just going to call it f and g, f times g would be first times derivative of the second plus second times the derivative of the first. Everything is going to go back to that limit definition. So remember that the limit definition is taking the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So I'm going to apply that to the functions f times g. So it's going to be f of x plus delta x, g of x plus delta x. So there's my substitution of replacing x with x plus delta x, minus f of x, okay, which is going to be minus the original thing, which is going to be f of x times g of x. And all that's divided by delta x. So here's the trick to this. What we're going to do is we're going to add 0 in a fancy way. And that's a common trick when we're talking about deriving things. So we're going to have f of x plus delta x times g of x plus delta x. And this is where we're going to add 0. So I'm going to subtract f of x times g of x plus delta x. And I'm going to add the same thing. And I still have the minus f of x, g of x hanging out, and everything's still divided by delta x. Okay, so what I've really done is I've added 0 here, which isn't changing the problem. And the reason I needed to do that is, remember, I need to rewrite everything in terms of derivative notation. So I need to get it somehow into this kind of form. So that's the goal. So now we're going to do some fancy grouping here. I'm taking the limit as delta x goes to 0. So notice that these two terms have that g of x plus delta x in common. And that's going to leave me with the f of x plus delta x minus f of x. And all of that's over delta x. And then these two terms, notice they have an f of x in common. And that's going to leave me with g of x plus delta x minus g of x all over delta x. So now we're going to think about how can we rewrite this using limit properties from chapter 1. So the limit of the product is the product of the limits. Same thing here. Remember, in this step, we were taking the limit of all of that fun stuff. really don't need those brackets there. So now let's take the limit of each of these pieces. The limit as delta x goes to 0 of g of x plus delta x is going to be g of x plus 0, which is just g of x. This is the definition of the first derivative of f of x. Plus, this limit would be f of x. And this would be the definition of g prime of x. So we said that in the beginning that the derivative, and I'll call it y prime, is going to be equal to that. So there's our derivative. And you can see that that's what our goal was up here. So now that we have that derivative and we've derived it, let's work some examples. Suppose we have y equals 3x squared times sine of x, and we want to take the derivative. So the product rule says it's the first function, which is 3x squared, times the derivative of the second. Now, I'm not going to take that derivative yet. I'm just going to write it in notation that says, hey, I need to remember to take the derivative. And that's what this notation does, is if it's in the brackets with that little apostrophe here, it means you need to take the derivative of what's inside. So first times derivative of the second plus the second times the derivative of the first. So there's my setup. And now we're going to take derivative. The derivative of the sine is cosine. The derivative of 3x squared is going to be 6x. And now we're going to clean it up. So this is setup. Take derivatives. And then clean up. So I've got 3x squared cosine of x plus 6x sine of x. And if I wanted to be fancy, I could factor out a 3x from all these. So I'm left with 3x times x cosine of x plus 2 sine x. There's my derivative. So notice my notation here. I do have the derivative of this. Okay, let's do another one. And this is where you may want to pause the video, take the derivative, and then come back and check your answer. So notice that we're going to have to use the product rule on this piece. This guy's going to be easy. It will not require a product rule. So the product rule says it's the first one times the derivative of the second. Notice I have not taken that derivative. That means I need to take the derivative of what's inside the brackets. First derivative of the second plus second times derivative of the first. And then the derivative of this guy is going to be the derivative of sine, which is cosine. So here's my setup. Okay, setup because this is the setup for that product rule. Product rule was needed in that first piece. First derivative of the second plus second derivative of the first. And then I took the derivative of this guy. So now we're going to take derivatives. Derivative of the cosine is negative sine. Derivative of 2x is 2. So that's where we take derivatives. And then now we're going to clean up. So I have negative 2x sine of x plus 2 cosine of x minus 2 cosine of x. Notice that that reduces. So my derivative is negative 2x sine of x. So there's our product rule. First times derivative of the second plus second times derivative of the first. So now let's move on to the quotient rule. Quotient rule is when we have two functions that are divided and we want to take a derivative. Quotient rule says it is the bottom function times the derivative of the top minus the top times derivative of the bottom, all over that bottom function squared. Now, if we wanted to derive this, it would be really similar to the way we derived that product rule. We would end up having to add and subtract something and then do some factoring like we did here to get it in there. I'm not going to derive that one on here, but we could if we wanted to. It would go pretty much the same way. You can check the textbook for a derivation of that one. So let's look at a few examples. Suppose we had the function y equals 5x minus 2 over x squared plus 1. So when I take the derivative, we're going to do our setup. It's the bottom times the derivative of the top. So I'm going to set it up first. Once again, this means I need to take the derivative of what's inside the bracket. Bottom times derivative of the top minus the top times the derivative of the bottom, all over the bottom function squared. So there's my setup. So now we're going to take derivatives of what we need. So I need to take the derivative of inside the bracket. 5x minus 2 has a derivative of 5. The derivative inside of the brackets here is 2x, all over the bottom squared. So this is my take derivatives. And now we're going for the cleanup. So be careful when you're doing the cleanup. Make sure you distribute things properly. So I'm going to distribute that 5x to everything in that first parentheses. Or sorry, the 5 to everything into the first parentheses. I'm going to distribute the 2x here. So that's 10x squared minus 4x. Notice I kept it in parentheses because I'm going to have to distribute that negative in front. Over x squared plus 1. Quantity squared. I am not distributing. Do not distribute here or FOIL or whatever you want to do, however you want to call that. The reason we don't want to do that is because we're hoping that something will cancel with the denominator. In some cases it does, in some cases it doesn't. Either way, we want to keep it written as concisely as possible. So let's combine some like terms here. So we have 5x squared plus 5 minus 10x squared plus 4x all over x squared plus 1 quantity squared. Combine weight terms, we have negative 5x squared plus 4x plus 5 over x squared plus 1 quantity squared. So with this one, it doesn't look like we're going to be able to factor anything and cancel anything. So there is our final answer for that one. Let's do another one. Suppose we had f of x is equal to x over sine of x, and we need to take the derivative. Derivative would be bottom times derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So there's my setup. I'm going to take some derivatives. Derivative of x is 1. Derivative of the sine is cosine of x over sine squared of x. And then we're just going to clean it up. So we have sine of x. Oops, I forgot the x right here. So sine of x times 1 is sine of x minus x cosine of x all over the sine squared of x. Okay, it doesn't look like we can simplify anything either, so that is our derivative of f prime of x. So we've looked at product rule, quotient rule. Now let's look at some derivatives of trigonometric functions. If we want to take the derivative of the tangent function, it's going to be equal to secant squared. The derivative of cotangent is negative cosecant squared of x, or negative 1 times cosecant squared of x. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. So we could derive any of these really using that quotient rule. So for instance, what if we wanted to take the derivative of cotangent of x? Let's do that one. Well, cotangent is the same thing as cosine over sine. So using that quotient rule, it says it's the bottom times the derivative of the top minus top times derivative of the bottom over the bottom squared. So there's my setup. Now if we were to take derivatives, derivative of the cosine is negative sine of x. Derivative of the sine is cosine. So we have negative sine squared x minus cosine squared x over sine squared x. And this almost looks like a Pythagorean identity in the numerator. And in fact, if we factor a negative out, we will get the Pythagorean identity. So that's equal to negative 1 over sine squared x. And that is equal to negative cosecant squared of x. And that's what we expected to get. And we could derive all the other ones in the same manner. So let's look at another example. Let's say we wanted to take the derivative of square root of x times tangent of x. This would be a product rule. So think about your setup. It's the first times the derivative of the second plus the second times the derivative of the first. So now we're going to use those rules. We know the derivative of the tangent is secant squared. We just talked about that one. The derivative of square root of x, we actually need to think about that as x to the 1/2 power. So when we take the derivative, we bring the exponent down, we subtract 1 from the exponent. So now we have the square root of x, secant squared of x, plus 1/2 x to the negative 1/2 times tangent of x. So now we're going to do some fancy factoring. I'm going to rewrite this as x to the 1/2. So these two terms actually have an x in common. We could factor out an x to the negative 1/2 power there. In fact, I'm going to factor out that 1/2 also. So let's think about what's going to happen when we do that. If we factor a 1/2 out of here, we're thinking about what do we need to multiply by to get that coefficient of 1. And we would need to multiply everything by 2. Because 2 times 1/2 would give me that 1 as the leading coefficient there. Now, if this were an x, then x to the negative 1/2 times x would give me the x to the 1/2 power there. And then we're going to have that secant squared of x. And then notice that we factored both of those out. So that's going to leave us with just a tangent of x here. And then we could actually rewrite this, clean it up just a little bit more. That 2 is in the denominator, and this guy belongs in the denominator also. I'm going to write out square root of x. So there is our derivative. So let's do another example. Suppose that the directions are different. Suppose the directions say, find the equation of the tangent line to f of x equals x over x plus 4 at the point -5, 5. So this is going to require several steps. First, we got to find the derivative, because to find a tangent line, you got to have two things. You got to have a slope and you got to have a point. So the slope is going to use the derivative. In this case, we're going to evaluate it at -5. And then we have a point, so we can find the equation of the tangent line there. So let's get started. To find the derivative of f of x equals x over x plus 4, which is what we're looking for, we're going to use the quotient rule. Quotient rule says it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So there's my setup. Now I'm taking derivatives. So bottom derivative of x is 1. Minus top derivative of x plus 4 is 1 over that bottom squared. Simplify. We get x plus 4 minus x in the numerator over x plus 4 quantity squared. That's going to give us a 4 over x plus 4 quantity squared. So our slope of the tangent line would be equivalent to the derivative evaluated at our point, and we're looking at an x-coordinate of -5. So we're going to have 4 over -1 squared, which is going to give us a positive 4. So we have a slope, we have a point. Now we can use point-slope form. So we have, and then the point, I'm just going to rewrite it down here so I don't have to keep going up, is at -5, 5. So we have y minus y1 equals m times x minus x1. Y minus 5 equals 4 times x plus 5. So y minus 5 equals 4x plus 20. And y is going to be equal to 4x plus 25. So there is our tangent line to this graph at the point -5, 5. So if we move over the Desmos so we can see exactly what we've done. We've got the graph, y equals x over x plus 4. So that's this blue graph here. The point that we're trying to find the tangent line to is the point -5, 5. So you can see that point here on the graph. And we found the equation of the tangent line. Remember, that tangent line is going to touch that graph at that point -5, 5. And there's that tangent line. So that's exactly what we've done. We've taken this graph, we isolated a point on it. We're asking, what's the equation of the tangent line? How would I find that? Find the slope, plug in the point using that point slope form. Okay, the last thing in this section has to do with higher order derivatives. It turns out that we can take higher order derivatives, and all that means is I can take a derivative of a derivative. So first derivative, when we looked at notation, looked like this. Y prime or f prime of x, we looked at it as dy over dx. Remember, these mean we want to take the derivative of. So d over dx of f of x means you want to take the derivative of f of x. You do not have the derivative yet. The difference between the last two columns and these columns is that this says you already have the derivative. It says this is it. This is the derivative. And we did see another one here where we had f of x and it was inside a bracket with that prime. That's just a shorthand notation that says I want to take the first derivative. You only see this with the first derivative. I've never seen it with anything beyond that. We use that for a setup for the product rule and quotient rule. Second derivative notation is going to have a double prime here. Okay, or you're going to see a 2 here when you take the derivative. Now notice the placement of the 2. What's happening here is you want to take the derivative of dy over dx. So you can kind of see where that notation's coming from. That dx quantity squared there. This means you want to take the second derivative of what's inside that bracket. And then we can extend that to the third derivative. So notice we have those prime marks again here. Beyond the third derivative, you don't really see prime marks. And we'll talk about that here. Fourth derivative. So notice we've gone to a 4, but we've got parentheses here, and it's in the exponent. Okay, so it's not really an exponent. It's a notation for the derivative. Okay, it's just in the place where an exponent would live. So you've got that fourth derivative. This just means you have the fourth derivative. This means you want to take the fourth derivative of whatever follows. Now, occasionally, you will see this written in Roman numerals. We'll do that occasionally. Fourth derivative, you don't really see the Roman numerals. So you may see that written that way with parentheses around it. Okay, so, and we could keep going. We could take the fifth derivative, sixth derivative, seventh derivative, and so on. Now, as far as physics applications go, we don't really see anything past the third derivative. So the original function, we talked about the position equation in a previous video. If we take the derivative of position, we get the velocity, and this is the instantaneous velocity. So it's what the velocity is at a particular moment in time. If we take the derivative of velocity, we're going to get the acceleration. Now, in physics, if you take the derivative of acceleration, you get something called the jerk. And you could talk about what that is in terms of physics, which goes a little beyond what we're going to talk about in this video, but it does exist. So let's look at an acceleration problem. The velocity of an automobile starting from rest is modeled by the equation v of t equals 100t over 2t plus 15. V is measured in feet per second. T is time in seconds. They're asking us to find the acceleration at 5 seconds, 10 seconds, and 20 seconds. So to find acceleration, we have to figure out what is first the acceleration equation. And if this is our model for velocity, we're just going to take that first derivative there. It's going to be the bottom function times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So now I'm going to take derivatives. The derivative of 100t is 100. Derivative of 2t plus 5 is 2. So we have 200t plus 1500 minus 200t over 2t plus 15 squared. So we're going to get 1500 over 2t plus 15 squared. So this is going to give the acceleration at any point in time. So let's say I want to find it for 10 seconds. All I'm going to do is substitute in. So this is going to be 20 plus 15, 35. So I have 1500 divided by 35 squared. I'm going to compute that off screen, and that is approximately 1.22. So there's our acceleration. So the last thing I want to do is just to show you taking subsequent derivatives. So let's say we have the function y equals 7x to the 5th plus 2x squared plus 3x plus 1. Okay, notice this is a polynomial. So let's say I want to take the first derivative. So remember, we bring the exponent down, subtract 1 from the exponent, bring the exponent down, subtract 1 from the exponent. The derivative of 3x is just 3. The derivative of 1 is 0. So if I wanted to take a second derivative, taking the derivative of the previous answer, so we're going to have 35 times 4, which is 140. So we brought that exponent down. Now we're going to subtract 1 from the exponent. The derivative of 4x is 4. And the derivative of that constant 3 is 0. If I wanted a third derivative, I would bring that exponent down. So 140 times 3 would be 420 x squared. The derivative of 4 is 0. And I could keep going. If I wanted to take the fourth derivative, and I am going to use that Roman numeral notation there. That's what I'm used to. Bring the exponent down. Subtract 1 from the exponent. I could take the fifth derivative. And then I could take the sixth derivative. What's interesting about polynomials is that we could keep taking derivatives, and eventually with a polynomial we'll always get to 0. Now that's not true with other functions, but it is true with that one. Let's do one more. Suppose we had x cosine of x. And let's just find the second derivative. So you got to start by taking the first derivative. So it's the first times the derivative of the second, plus the second times the derivative of the first. So there's my setup. Take the derivative. Derivative of the cosine is a negative sign. Derivative of x is 1. Clean it up. So I have negative x sine of x plus cosine of x. So if I want the second derivative, I have to take the derivative of this guy. So second derivative, notice the notation that I'm using here. Still going to be a product rule. So it's the first one times the derivative of the second. So here's my setup. Plus the second times the derivative of the first. And then I'm going to take the derivative of the cosine, which is negative sine. So setup. Let's take derivatives. Derivative of the sine is cosine. Derivative of negative x is negative 1. And then let's clean it up. There it is. So there is our second derivative for that particular problem.